Okay, let's start. Sorry, no, I'm sorry that I'm a bit late today. Okay, let's just start. So, actually I wanted to skip this. I mean, actually I didn't even want to talk about superfluidity, but last time some people asked me about what, we were always talking about fermions and what the role of bosons would be in a neutron star. And so I thought I'd at least quickly mention this, because maybe on the alpha later on we'll maybe talk about glitches, I don't know, and so it might be useful to have a bit of say, background on that. Okay, so okay, no, maybe this is a problem. Okay, here we go. So, right, so I just quickly want to tell you that there's even a bit more about the other forms of matter that could exist in a neutron star. And what could happen? So far we always talked about fermion existence, right? You have fermions at very low temperatures, and then they degenerate and fill up all the Fermi sea, say all these different states. But what we neglected so far is interaction. And surely first of all, this somehow changes the Fermi sea a bit, and there will be a different Fermi momentum if you have interactions. But even something more dramatic can happen, because when you have fermions and they're interacting, what you can actually do is you can form a bound state of that fermions. And it can happen that this bound state, or rather naturally it happens, that if you have two fermions and you bind them, that the statistics of these particles changes. I mean, you remember a fermion is something where you have a two-particle state and you interchange the particle, then you get a minus sign. Now, if you have two of these fermions and you bind them and make a new particle out of that, you can rather easily see that somehow this minus sign then cancels, and these new particles, they behave as there would be bosons. That means if you interchange them, you don't get a relative minus sign. And due to this, they have very different properties. So people might know this because the same thing can happen in ordinary superconductors in the lab. There you have a rather small, indirect, attractive interaction. Here in a neutron star, you have a rather strong interaction that's very direct. You don't, I mean, if you heard about this in ordinary solids, the interaction is via something called phonons. That's you need a lattice, and you need to have somehow modes in that lattice, and you would only form very weakly bound states in such a case. Here you would have very strongly bound states, and they are called, in general, called Cooper pairs. I mean, these states that you can that you get when you bind two fermions that are close to the Fermi surface. And the picture is kind of this: you have two particles here, basically on the opposite side of the Fermi surface, and they interact and scatter into two new particles. And since the low energy states are all near the Fermi surface, everything else is blocked, you get this very characteristic interaction here, and you form something called a Cooper pair. And as I said, they are bosons, and bosons do something very different from fermions. They don't pile up, but they can all go to the same state. And if you had some quantum mechanics class or some quantum statistics class, you might have heard about something called a Bose-Einstein condensate. That just means all of these bosons piling up in the lowest energy state. And exactly that's what happens here. So he would somehow remove these states close to the Fermi surface, these are the red guys, and they would then form bosons, and somehow they are not fermions anymore, so you wouldn't even have them on that plot here anymore, and they would form a separate condensate of bosons, and this is called a Bardeen-Cooper-Schrieffer condensate in the simplest case. And the important point is that the states that contribute, they live very close to the Fermi surface in general. I mean, there is something called delta, which is called the gap, and these states within a distance of delta to the Fermi surface, they would contribute and form bound states that condense. But the important point is, in general, this delta is much smaller than the Fermi momentum. So it's really just kind of a small effect at the surface of the Fermi sea. That means you still have a lot of pressure here from the entire Fermi surface that will stabilize the star, but just a few of these fermions would somehow condense and form this additional condensate. Now, that means as far as the equation of state is concerned, this doesn't have a big impact because the pressure still comes from the fermions. So as far as the equation of state is concerned, it's very similar. But what this does is that all the states close to the Fermi surface, they're not there anymore. These are the guys that actually form bound states. They're kind of gone. That means we don't have any low-lying fermion excitations anymore. And correspondingly, you don't have any low-energy processes in this material. And that's what somehow gave the whole process its name, because what this means, usually when you have a fluid, you would always have interactions between the particles, and you have some nice directed motion, and when some interaction happens, you somehow transfer this nice mechanical kinetic energy of the particles into random motion, which is basically heat. And that's called dissipation. You basically would that's why usually an ordinary fluid does not flow forever, not perfectly, but there will always be dissipation. So if you have a bucket here and I start steering, at least after a minute, everything will stop moving again, right? In a superfluid, that's different. Since there are no low energy particles here, there is actually no dissipation. That means that the fluid actually flows without any friction. And the reason for this is that what flows is basically the superfluid. I mean, you basically have a macroscopic quantum state that presents the fluid, and you don't have any low energy degrees of fluid freedom that could dissipate energy. And that's in this picture, that's why this is called the gap, because there's simply no fermions that could actually dissipate energy, or that actually, and so that's kind of the idealized case. If the temperature really vanishes, if you have a finite temperature, then you still have some ordinary fermions, because you can somehow break these Cooper pairs. There's some strong interaction, but if you have a temperature, means the particles have some energy. That means every once in a while, the particles have enough energy to break one of these Cooper pairs. And in this case, you have low energy excitations that can actually dissipate a tiny amount of energy. The point is only, it's really exponentially suppressed. That means so due to this pair breaking, you would have some ordinary component on top of the superfluid, but this component is suppressed in the gap over the temperature in this exponential way here. And that means if the temperature is very small, this factor here is arbitrarily small. That means at low temperatures, the superfluid really behaves basically as a perfect superfluid where you don't have any dissipation whatsoever. But if you start to heat it, it becomes more and more normal again. Okay, superfluids are also interesting because when you try to steer them, when the superfluid rotates, it behaves very different than an ordinary fluid. I mean, if you here in ordinary fluid, the entire fluid moves, right? But as I said, this superfluid is a condensate, that means it's a macroscopic quantum state, and that state cannot rotate. It's kind of the ground state. Rotation would always be some energy on top. You cannot get this ground state to rotate. And correspondingly, what happens is that in the superfluid, you somehow make small vortices, these are these guys here, made of ordinary fluid. Somehow you punch a hole into this superfluid. There you have ordinary fluid that can rotate, and that's what you get. So you really can get discrete vortices that will somehow take over the angular momentum that you give the system when you stir it. So the condensate itself is untouched basically, but somehow it's these holes, these vortices which take over the angular momentum. And the cool thing is you can actually see this in a lab. I mean, this is somehow the picture where they form a superfluid in a lab and then stir it. And then you actually see these guys. You actually see 1, 2, 3, 4, and so on vortices. They're discrete, they're quantized, they carry a fixed number of angular momentum. And this is really cool because usually you can never actually make a photo of a quantum state, right? You never see it. They're so feeble. If you make any disturbance to the system, the quantum state will decay, or you will measure it and then you cannot really see the quantum state. In this case, since this is a macroscopic quantum state consisting of many, many, many particles, and there are no low energy degrees of freedom, you can actually see it. You can really observe it, and yeah, that's what people find. And this is very important because in a neutron star, surely we also have a lot of angular momentum if it rotates. And if there's a superfluid, then this can lead to rather unexpected behavior because such a superfluid cannot lose its angular momentum easily. It can only do this in a quantized way, and therefore this can lead to interesting effects, and I guess Ali Alpa will talk about this later on. Okay, another thing where superfluidity is important is, I mean, it's basically the same. The only difference is if you have now charged particles that become superfluid, that means they carry a charge. That means, in this case, superfluidity is basically superconductivity. You conduct a current without any friction. That means, yeah, it's a superconductor. And in this case, you would measure no electric resistance. And in this case, you can have different types of superconductors. Probably I won't go into the details here because we don't have enough time. But this can also be very important when you have very strong magnetic fields, as in a neutron star. You could also get observable effects from this kind of superconductivity. But okay, as I said, just because of the time, I will skip this. Okay, so what's more important is where would we expect to have superfluidity or superconductivity in a neutron star? And before I already gave you this picture that the nuclear force between neutrons and protons has somehow two different regimes. It's attractive at intermediate distances when they're still reasonably far away, but once the nucleons get very close to each other, it becomes very strongly repulsive. And just from this simple picture, from the forces between the individual nucleons, one can somehow understand what's going on when I look at. One can somehow, understand where we would expect superfluidity to happen. And surely it's then a density-dependent phenomenon, because the density tells us how, on average, how close these particles are together. That means in which regime we are here, right? And due to this, what we find is that in the inner crust of a neutron star, where you have a neutron fluid, the neutrons can actually pair. I mean, they are in this attractive range here of densities, and you can get pairing in somehow the simplest way, don't worry what this means in detail, they can easily pair. The protons have a lower density, that means you don't get proton superconductivity there, you just get superfluidity of neutrons in the inner crust where the density is well, reasonably high but not very high yet. If you go to higher densities, that means the core of the star, deep inside, the density rises, and in this case the protons, which actually have a lower density than the neutrons, basically get to that regime where the distance between two protons is right, that the interaction becomes attractive. And then you get proton superconductivity in the core of the star. And in even higher, if the density gets even higher, I mean, in this case, in the core, the neutrons cannot easily pair anymore. They get into this regime where they get so close that you're kind of in this repulsive regime, and in general, then you don't get any pairing. But actually, what turns out is that you somehow you cannot pair them easily, but there's somehow higher quantum states. This is the so-called P-wave, and this interaction here somehow depends on the channel you look at it. I mean, this is the simplest picture, but if you have quantum states, the interaction also changes for depending on the quantum numbers of these two particles. And what one finds is that the neutrons can actually pair in some other quantum state at higher densities. And this is also important because this could mean that in the core of the neutron star, both protons and neutrons are paired, and that would have very strong impact, as I said, on the low energy degrees of freedom, because there wouldn't be any. And this would strongly change the properties of such a star. Okay, so this is kind of, one can also do computations, and then people find actually this would be the gap, and as I said, it's a function of density. It will be maximum at the density where they have just the right separation, that the attraction between them is maximum, and that's what we find. We somehow get this kind of peak-like structure that at a certain density you get a lot of pairing, and correspondingly this gap here is very big. Okay, and so just to mention it, in principle we talked about quark matter last time. You can also have something very similar in quark matter. The interaction is not electromagnetic in this case, or like in an ordinary superconductor, but it's actually the same strong interaction, and correspondingly it's called color superconductivity. And so in this case, you actually have attractive interaction between these quarks themselves at very high densities. And the important point here, I mean, I don't want to go into details, that the main important point is that, as I told you, at really high densities, the interactions between these quarks become weak, right? It means at really high densities, we know what happens. We can actually solve the theory, I mean, at ridiculously high densities, that might not be reached in a neutron star, but still, we know what happens in the asymptotic high density limit. And there people have shown, and we can actually prove it, that the preferred state of matter at asymptotically high densities is just a so-called color superconductor, where you also have pairing of these quarks close to the frequency. And as I said, I don't want to go into details, I just want to mention it because if I already talk about superconductivity, it makes sense to mention that this can also be relevant for quarks. Okay, so now we talked about many different phases of matter: hadronic matter, quark matter, superconducting phases, many different of them. And as you know from ordinary matter around us, matter itself can have different forms, right? I mean, it could be solid or liquid or gaseous. And this is kind of the standard phase diagram that we know from ordinary matter, where we have all these different phases. And in general, at high density, when you have different forms of matter, different phases, you can also draw such a phase diagram. And you can think of what would happen as I increase the density, for instance. I mean, this is a phase diagram in pressure and temperature. At high density, the relevant quantity is not the temperature, but the density, as we discussed. And one can draw a similar diagram for high density matter. And as we'll see, it will have very similar structure or ingredients. I mean, what you know from the ordinary phase diagram is that there are these phase transitions here, and there are critical points and so on. And the phase diagram of high density matter has a similar structure. So let's quickly talk about phase transitions. I mean, a phase transition basically going from a solid phase to a liquid phase. If you remember your thermodynamics courses, this is described by something called an order parameter. And it's just a quantity that has a certain value in one phase and a very different value in another phase. So basically something that allows you to distinguish these two different phases. And in our case, this could be, for instance, magnetization, or if you have superfluidity, the superfluid condensate, or it could be we saw there are phases that have these hyperons. That means particles involving strange quarks, or quark matter would involve strange quarks. So strangeness would be such an order parameter. So any parameter with which you can clearly distinguish two different phases. And then you can somehow classify the different transitions between these two phases. And in general, what you need is to have a phase transition is that this order parameter is somehow discontinuous between one phase and another. And it really chunks. And the simplest case is a first order transition. There really the order parameter itself has a chunk. And there's also something called a first order phase transition, where the order parameter is continuous, but if you look at the derivative has a chunk, or the order parameter itself would have a kink. And these can be very different. I mean, these different phase transitions can have a very different impact on the properties of the star. And the last one, which is actually not a phase transition at all, is if you don't have any discontinuities, that's called a crossover. That means in this case, the order parameter will go continuously from one phase. Quickly draw this. I mean, so let's say that's the order parameter. This is whatever quantity I want to change, say the density. I mean, the first order phase transition would be something like this, where you really have a clear charm. The second order phase transition would be something like, like this, where you have a kink here, and a crossover would be something where you just go from here to here, and everything is smooth. Alright, so this would be somehow the value in the one phase, this is the value in the other phase, and you can have different ways going from this value to this value. Okay, and what's most interesting are first order phase transitions, because first order phase transitions can lead to something called mixed phases. And the reason is that in the case of the first order phase transition, we have something called a coexistence region. And the reason for this is that if you look at the thermodynamic potentials, and this is the order parameter, what you find is that there are kind of two minima here. So that there's one that's preferred at some value of your parameters like density here. If you're below a critical value, you have this picture, and the critical value, these two minima are exactly equal, and if you even increase your parameter higher, like density, all of a sudden the other one is preferred. And again, if you kind of start out here and you go to here, there will be some, I mean, your system won't abruptly go from here to here, right? I mean, you would somehow have to transform the entire system, and the entire system transforming all of a sudden is not very likely. You would somehow have to cross that barrier here, and that's not something that happens. And so what we actually have is something like, you might have heard about say in case of a liquid gas transition, you can have if you increase, if you go from one phase to another, you can run into a situation where you have exactly this picture, right? Where you somehow have something like undercooled gas, where the gas won't really want to go to the liquid phase, because what you need is you have to form droplets, and droplets require additional energy because they have a surface which costs energy, and so it can happen that actually if you stick in the gas phase, you don't really form these droplets. I mean, it really depends on the boundary conditions. If you have a lot of dust in the air, for instance, then these droplets can condense on small dust grains, and then you much easier get that condensation and water condensing. But otherwise, you can really be stuck in the wrong phase, and that's interesting because then you can have something called coexistence region in a neutron star. Now, remember, in a neutron star, we would go from here to here by increasing the density. That means all these different stages here are realized at the same time, somewhere in the neutron star as the density increases once you go towards the interior. And correspondingly, what you get is one of these two situations. It depends on the surface energy or the surface tension. If the surface tension is very big, then you don't want to form these small droplets, and then you will stay in such a situation where you somehow have a sharp boundary between the two different phases. But if the surface tension is small, it only costs a small amount of energy to have additional surfaces there, then you can actually produce something like this, where you have droplets of one phase in the other phase. That means that would be a mixed phase where you can continuously transform as you go. As you increase the density, you gradually transform your system from one phase into the other phase. And as I said, that can have very different properties of that star when it comes to all kinds of things like heat transport, and then all kinds of properties of the material inside can be very different in these two cases here. So that means, okay, we already talked about many different phases. As I said, we could even have mixed phases and even more complicated. And this is somehow what I told you about, that you can actually then also draw a phase diagram for high density matter. And that's the main characteristic of that we know so far, how it should look like, but there's a lot we don't know. So we know at ordinary densities that we know, I mean densities in nucleus, we know what happens. We have hadrons, neutrons, and protons, and that's somehow where we can make measurements. But as you go towards neutron stars, the density gets bigger, that's the binary density here. The other axis is temperature, but as I told you, neutron stars are a very cold system, so people can also somehow probe the high temperature axis, and they do this at the colliders. But as far as we're concerned, for neutron stars, they're basically interested in this axis here. Basically T nearly zero and very high densities. And the only thing we know is that neutron stars are at some density range. And the only thing we actually really know is that at really high densities, the preferred form of matter will be some form of quark matter, called superconducting quark matter. But we don't know which of these other phases are realized in between, and that's exactly the range of densities that's realized in the neutron star. So we don't really know what's going on. We have many possibilities, but we cannot really so far resolve the situation and say, okay, this will be there, this will be there, but so far everything goes in principle. All this could be potentially present there, and we have to figure out what's actually realized. And just to give you
what is the gap about
sorry, this? Okay, yeah, this is just to symbolize that this phase here is only realized at ridiculously high density. So this just means, okay, well, we go from 1 to say 5 or 10 times saturation density, that's where neutron star lives. And this, when we really know what's going on, would be at 1,000 times saturation density. And just to make a point, it's like, okay, let's cut here and glue them together somehow. I mean, if I would actually plot this, this would be over here, right? So that's all it says. Okay. So, and just to show you that it's even a bit more complicated, in reality we don't just have density and temperature, but we also have something called isospin chemical potential, or say proton fraction is another parameter. What's the chemical composition? We talked a lot about this. How many protons do we have in the system? And this will be somehow another axis that also, if you go along that axis, you also can have different phases. And so it's even more complicated, and a neutron star actually would be not on that axis, but somehow displaced here, where you somehow have a certain number of protons in the game, or at least a certain number of charged particles in the game. And so it's even more complicated to determine what the matter in the neutron star is made of. Just to give you an idea, okay, this would be high temperature, we have many inches in high density. To give you an idea of what the possibilities are, is here somehow a few models that people came up with. They just have their model systems, and then they compute a phase diagram. And this is kind of, and that's a very old version of it, that's somehow 20 years ago. And they get more and more fancy all the time. I mean, you see all kinds of phases of fourth matter that could arise here.
Sorry, can I ask a question?
Yeah.
All these high density scenarios, they always suggest that there should be exactly one scenario that follow all neutron stars, or there are some other ideas that could be more than one possibility.
Very good question. So there will be one equation of state, and there will be one. There's the phase diagram. So once I go along this equation of state, which, as I said, will be complicated because it will go at some funny line here in this three-dimensional space, right? And along that line, there might be a few different phases lined up. But there's one unique equation of state, and there's one unique phase at each density. So surely neutron stars are different. You can have a very heavy star, you can have a very light star. So you could have different stars made out of different materials, but the equation of state and the phases that in general appear as you zoom through the densities, that's a unique property of nature. We just don't know it yet. If we would know which equation of state is realized and which phases are realized, let me plot it in some steps once again.
Does it absolutely change if it's all hyperons or all three quarks? Exactly, the equations should be similar.
There are cases when it's similar. In this case, it's not so similar. For instance, quarks are very light degrees of freedom. Hyperons are very heavy.
Yeah.
They have very different properties when it comes to Fermi pressure. They will give you a different equation of state. There are other scenarios, as I said, for instance, superconductivity, that will very weakly affect the equation of state. But it will very strongly affect the low energy properties of the star. If you talk about, say, what radiation does that star emit? How does temperature in the star flow? How is it equilibrated? Things like that. That will be very different because that depends on the low energy degrees of freedom. So just to make that point once more, so this would be the equation of state, say for instance, pressure as a function of density. And as I said, there will be one unique curve, and it might consist of several parts, right? It might do this and, well, whatever, right? And there might be different phase transitions here and different phases that actually are realized. But there will be one curve, not several. We just don't know. That's what we want to figure out. Which phases and which equatorial states actually realized. Okay, so I just want to give you a quick flavor that so far we just don't know. You know, I mean, people come up with more and more fancy and more baroque plots with hundreds of, or really many of different possibilities, and usually they don't include everything. They just include a certain set of potential phases. I mean, in this case, they, for instance, say, okay, we look at quark matter, they don't even include all the hadronic phases here. So in reality, it's really extremely sensitive to all kinds of details that we don't really have under control yet. And so the point I want to make here is, from a theoretical point of view, we cannot resolve this right now. So what we would like to do is resolve this observation. So if we have observations of neutron stars, then the chances are much better to actually learn something about this curve, what it actually is, and in particular what phases it's made of, than if we would actually try to come up with some model and solve it, because it depends so strongly on all these model assumptions that we don't have under control right now.
Okay. So also, do we have an idea these phase transitions have which observational properties that we can observe? Do we have an idea about that?
You mean if the star would actually transform because it's pushed over one of these density boundaries here? Yes, some of them definitively do. If you would somehow transform a neutron star into a quark star, you would release a lot of energy, and you see that is something you might really see here. In other cases, it might be much milder. As I said, if you just produce a superfluid inside, that might not immediately change much. I mean, it might change the long-term properties of the star, but it might not give you an instant, huge amount of, instant dynamic blast or something that you could see. But yeah, that's the idea. I mean, in principle, we have ways to probe it, either by systems that actually have such a phase transition, or simply by observing properties of stars and then relating what we see to the properties of one of these phases here, because these phases have very different low energy properties. For instance, some might emit a lot of energy into neutrinos, others won't at all. And this way, just from an equational state, it's rather hard to distinguish different phases of matter, because many, as I already told you, many phases have rather similar properties, because they only change, for instance, the degrees of freedom close to the Fermi seed a bit. That won't change the equational state at all. But as I said, what it changes is the dynamic properties of the star, the cooling, the heating, I don't know, how it dampens oscillations, things like that. They're extremely sensitive to the degrees of freedom in the vicinity of the Fermi surface, to the interactions there. And correspondingly, all these material properties, they can vary drastically from one phase to another, and therefore they can be very different for different phases, and we'll come to that later. Okay, so that's what I wanted to say about, well, matter in these stars. And now let's actually talk about how we describe them. And I already gave you a simple picture in the Newtonian gravity, and which is fine for white dwarfs, where the gravity is not extremely strong, where you can say, okay, Newtonian approximation is good. But in a neutron star, it's very different. The gravity is extremely strong. You're really kind of close to the point where the gravity is so strong that not even the general Fermi pressure can actually sustain the star, and it might collapse into a black hole. And correspondingly, we really have to solve the system in general relativity, and that will be an equation called the Oppenheimer-Volkoff equation. That's what I want to talk now about. So let me, before I get into this, just quickly remind you, or if you never heard about this, give you some really back of an envelope intro to what general relativity means. So the idea is that gravity is basically geometric in the sense that it's described in something called a metric tensor, and all the metric tensor is it tells you how far are two objects or two points in space-time separated. It just gives you the separation. I mean, surely in here, in this room, we can just have a ruler and measure, but in space-time, it's not that obvious how far 2 points are separated. And what general relativity does is that it describes gravity in terms of the metric of space-time, or the how. I mean, if you have a flat surface like this blackboard, then it's clear, okay, how 2 points are separated. But if you think of something curved, if you would curve the blackboard, then the same 2 points might have a very different distance. And that's exactly what GR tells us, is that gravity basically comes due to some curvature of space-time. That the distance between 2 points is not the same as we know it from Euclidean space, but it can have a very different gravity. And this is, I just want to quickly make that point, because just to give you some kind of a reason why you might want to study this properly at some point, because this is really one of the coolest things I've seen, or the coolest thing I've seen in physics, and why I like doing physics, is you get all this theory that Einstein wrote down, basically from the same principle we talked about last time, or was it 2 weeks ago? Namely, all you say is that you don't want to be prejudiced when you describe nature, right? And it's exactly the same thing that we also do when we derive the other three forces we know in nature: the strong force, the electromagnetic force, and the weak force. Also, these theories built on exactly the same simple principles. That all you say is, I don't want to be prejudiced. I don't want to describe nature in a way that I somehow make any assumptions that I don't have any information about. And the cool thing, and that's really extremely remarkable, is that this simple principle actually gives you the answer. I mean, you would think, okay, well, if I assume that and say, okay, I don't want to make any assumptions, you have even less information, right? You don't know anything yet. But actually, in nature, it turns out that just doing that and formalizing this gives you the theory itself, which is pretty remarkable. In other words, it tells you there's only one way of describing a physical theory in some sense. And, okay, there's not only one, it turns out that there are a few ways, but in all these cases, that's what you do. And in case of general relativity, what you do is you say, okay, whenever I describe something in space or in time, I need coordinates, right? I say, okay, this point has coordinate, I don't know, 1, 3, 5, this one has some other coordinate. And all you assume here is that the physics should be invariant it shouldn't depend on what coordinates I choose. That's all you do. You just say, okay, well, it's arbitrary, I pick something, but the theory should not depend on that. And if you do that, then you somehow say, okay, the actual theory should be invariant under these coordinate transformations. They're called diffeomorphisms, but it doesn't matter. If I transform to any other coordinate system, it should be the same physics, and that actually gives you the dynamical laws. That's all you have to assume. Okay. Somehow, what you picked that is the simplest. You you get several options, and what you pick is the simplest version. That's what gives you general relativity. But that's what leads you to this equation, the Einstein equation. And what it does is, as I said, it connects this function, a function that tells you how far different points are separated, with the energy momentum tensor, basically something that tells you about how much energy is in a certain volume of space-time or at a certain point. And so what it does is that somehow energy or mass tells space-time how it has to curve, and the curvature of space-time tells matter how it has to move. That's basically the general idea behind general relativity, or behind this equation here. And what's different, I mean, in Newtonian physics, it's only mass that actually gravitates. In this case, the gravitational field itself also carries energy and also, again, curves space-time, and therefore it's kind of nonlinear. A nonlinear equation, not like the equation we saw before, namely the Newton equation, which is linear. This is nonlinear. That makes everything much harder. But you can then again solve this. I mean, write down an equation for the hydrostatic equilibrium and general relativity, and what we find is this set of equations here. And if you neglect these red boxes for a moment, this is basically what we discussed before, right? I mean, this is the hydrostatic equation that I derived. That's, well, just the mass and some volume, and that would be the corresponding equation for the gravitational potential. The only difference is now, if you do it properly and take into account these general relativistic effects, we get some correction mechanisms. These are these guys here. And as you see, I mean, this is basically exactly the same, and then you get some correction factors. And whenever we are in a system that's far away from a regime where general relativistic effects would come into play, then these are really tiny. You can just neglect them. It turns out that a neutron star, they're not tiny. They're not huge. They're not, say, I don't know, a factor 1,000 or something, but they're of the order of 2, 3, something like this. That means you have to take them into account. They can have some impact, but they're also not completely dramatic. They're not a game changer, but if you want to get it quantitatively correctly, then you have to take them into account. And as I said, I mean, this somehow makes it more complicated to solve the equation, but the idea how we would do this is exactly the same as before. Before I get into this, I actually first wanted to point out that in addition to these equations, as before, you also need an equation of state. That's somehow another input, that is this equation, this relation P of rho. Then pressure as a function of energy density, that's something we need. And what I also want to point out, because as I said, this equation here basically looks like the equation we had before. And this is the mass within some radius. And if I integrate this, I get something like this here. And this looks exactly, I mean, it's basically the same equation that we had in Newtonian physics. The point is only, this quantity is not the same as in Newtonian physics. In Newtonian physics, this was the mass. It was just the mass of the system. In general relativity, this function here also takes into account the field energy. Say, it's not just mass that gravitates, but also energy density that gravitates. And therefore, although it's still called M, this is not. I mean, okay, sorry, I should say, actually, this is the mass of the system. It's what you would call mass, the total energy of the star. Whatever it is at rest, that's what we would call mass. But in this case, it also includes effects due to the gravitational field energy itself. That means it's not the same as if I would just add up the number of the rest masses of all the particles in that star. But it also contains contribution due to the the strong gravity in the star and the fact that the gravitational field itself carries energy, and that's included in it. And therefore, this mass that you get will be somewhat different. It won't be just the so-called baryonic mass, the mass of just adding up all the particles, but it will be a bit bigger. Okay. And despite these correction terms, I can still solve this equation numerically rather straightforward and do exactly the same as before. I somehow start at some pressure P0 and then I integrate outward. And so I do basically the same thing we already discussed last time. I pick some pressure, some central pressure for the star, then I integrate outward, and I start when the pressure hits 0. Oh, sorry. This point, that's the radius of the star where the pressure drops to 0. So it's exactly the same way you would solve this equation, it's just numerically a bit harder. And what you get from this is again a one-parameter solution. That means a curve m of r. We already discussed this before. That depending on the total mass of the star, you will have a different star, obviously, with a different radius. You say one equation of state will give you a whole curve, m as a function of r. And one can also show that typically these solutions are stable as long as the m by the r is smaller than 0 and the m by the rho 0 is bigger than 0. That means the mass, this should be a big R, the radius. The mass drops as a function of the radius and it increases when I increase the central energy density. The point is, this is the typical solution, but there can be more complicated cases, and therefore this is not really, it's a rather delicate issue, when is such a star stable or not, and I had to drop the slides on that, because we don't have time and it's rather technical, but one can describe this properly, and actually it's more complicated. This is the standard case, but we'll see there's some situations where stars can be stable, although these conditions are not fulfilled, and the other way around. So it's a nice guideline, but it's not perfect. Okay, so the next thing that's interesting is that even though these equations are now much more complicated than before, you see that they look rather nasty, because of all these correction terms, and maybe I just should point out what they are. This is, for instance, a term where you have P over rho. Now P is somehow proportional to the, well, in some sense, to the kinetic energy of the system, right? Whereas rho is the total energy. And that means if your particles have a lot of energy, like these particles we're talking about that have a high momenta since they are degenerate, then this gives you a correction. This is somehow similar to that. This would be somehow an integrated version of this term, whereas this term here is somehow, what you compare here is something like 2m over r, and 2m is basically the mass, it's basically something called the Schwarzschild radius. That's the radius where the star would collapse to a black hole. So if the size of the star becomes, which is usually always bigger than that radius, if the star becomes so compact that the size is of that order, this term diverges and you will collapse to a black hole. That means that somehow is a term that knows about compactness. These terms more know about the different forms of energy in the star. But they all will give you some correction terms. And what I want to point out is that even though the equations are so complicated, they still have in some cases, an analytic solution. And people came up with very weird cases of solutions, but there are a few that are really useful. And one is called so-called Tolman-7 solution, and that's this one where the energy density basically quadratically drops. I mean, you start with some some central density, and then it basically quadratically drops, where this is basically a parameter. Now, in reality, in neutron stars, that's not the case. I mean, close to the funny thing is, if the density is constant, this would lead to an infinite speed of sound, which is obviously unphysical. It means this solution, in principle, is unphysical. In reality, the density will change slightly with the radius. But again, I mean, it will be very similar to the solution. So this solution is also very useful to approximately describe a strange star, even if it's not at face value, not really physical. Okay, now let's talk about the different classes of stars we could have. Or should we make it the way grammar? Great? Okay. Let's say R. I don't haven't watched I don't know what time it is. 2:36. Huh? 2:36? Okay, let's say 10 minutes. Okay, let's continue. Okay, since someone just asked me a question, I think I should clarify this point because maybe what I said wasn't really clear. So when I said before, the equation of state somehow basically depends on the entire Fermi surface, right? So when you compute the equation of state, you integrate over the entire, all the states in the Fermi surface. So before I made a point that some phases of matter modify the Fermi surface only modify the Fermi speed only very close to the Fermi surface state. This very thin region here. There they will be different. And my point was that does not hardly affect the equation of state. But what it affects is the interaction processes of particles close to the Fermi surface. And that means all dynamical processes we can detect or that we can observe are strongly determined by that. It won't change the mass or the radius, but it will change how much energy it emits, how energy is distributed in the star, all these things. And these are kind of dynamic processes. And that's very important because these low energy degrees of freedom, close to the Fermi surface, they can be very different for different forms of matter. And that's all I wanted to say here. Basically that even phases that won't change the equation of state can have very strong observational impact because they change everything except the equation of state. And the assumption is extremely drastic. And that's the same thing if you somehow look at an ordinary solid. The low energy physics, I mean how the solid emits light, how it absorbs light, things like that, that's all determined by phonons or something like this. There you don't really break the solid or put a lot of energy, but just a tiny amount of energy. Say one photon that's absorbed by a phonon. These processes are what's relevant for all the mechanical, most of the mechanical, all the optical properties and everything, we somehow, all the material properties of that stuff around us. It's all determined by these low energy processes. And that's the point I wanted to make. It's exactly the same case in a neutron star, and therefore, even those differences close to the Fermi surface here can have a big impact when it comes to any observational aspects of these stars. Okay, but now let me come to somehow different classes of compact stars. We already heard they could consist of various different forms of matter, but as far as their mass and radius is concerned, there are just a few different classes here. And we already discussed them basically 2 weeks ago, and let's just dive into this and talk about that. So, as I said, one has to solve this Oppenheimer-Volkoff equations numerically, and then what you get is basically a radial profile. That means, for instance, how does the pressure, or in this case what I plot is the density, but they're all related to each other. I mean, I could also plot the pressure here, and the curves would look very similar. How do they change with radius? And so the red curves here, that's a neutron star, and as you see, you start at some density, and then the density drops, and until it becomes very low. And so this basically horizontal part here simply means that the density on this linear scale drops to ridiculously low values. I mean, we know the density at the surface has to go to 0, and we saw the equation of state on, I think, the first lecture, which went over 20 orders of magnitude in density, and correspondingly, that's what you see. The outer layers of the star are very dilute. I mean, it's not dilute, they're still extremely dense as far as, well, terrestrial standards are concerned, but compared to the interior, they are much less dense. Many orders of magnitude. And as I said, it actually goes to 0 at the heart.
What is expected radius of a neutron star then it is?
The typical radius?
Radius.
Well, we don't know. We don't know. I mean, to get this, to get this curve, I have to make an assumption. I have to pick an equation of state. So I picked one. I mean, this is something. This is a rather standard equation of state, which is called APR. But you have to just, well, pick some model, right? We don't know what the equation of state is right now. And if you now use all the different models that people came up with, you get something between maybe even below 10 kilometers to more than 15 kilometers. That's kind of the range. I mean, to get a really large radii is rather tough. You need an extremely stiff equation of state, extremely high pressure. Whereas if the equation is too soft and you get to really low values, then gravity just collapses the star. That means there is some range of values within you expect something, but it's a rather broad range so far. And people are trying to narrow it down with observations, and we'll come to that later on. And there, by now, we have a somewhat smaller range. But still, it's not clear that we could say the radius is between, I don't know, 11 and 12 kilometers or something like this. This is what we want. That would be great if we actually would be at a point where we can say that. And it's funny, I mean, people make these observations, and all of them basically say, yes, it is 11 plus minus 1. But so far they don't agree. The other people who say, oh no, it's 14 plus minus 1, and that's a problem so far. Somehow they underestimate their uncertainties. But yeah, right now we don't know yet. It's in that ballpark, say somewhere between 10 and 15, but yeah, that's about it, what we know right now. Okay, but what I mainly wanted to show here is not exactly the precise values for the radius, but rather the generic properties. So this would be a neutron star, as I said. You go to 0 in pressure or density at the radius. It gets the outer parts are very, have not very high density compared to the core. But there are other options, and one is these strange stars that we talked about last time. This would be this solution here, and then you actually end at a finite density at the radius. It doesn't go to 0. And as you see, I mean, we discussed this constant solution. It's not that far away. As you see, it kind of goes down. That means there's no problem. The speed of sound is not infinite, but it's roughly constant. I mean, it doesn't change by more than 20% or something like this, so it's not drastic. And so these are the two that we already discussed. And there's another option that we also had already discussed. And these are so-called hybrid stars. And there you actually have a phase transition in the star. So the outer parts would be made of ordinary neutron star matter, that stuff here. So these are the outer parts. But then at some point you have an actual phase transition, and you can actually see it here. You really have a jump in density because you have a first order phase transition. And then the interior would be made of quark matter. This is this. These are these solutions where you have this actual jump. Now, as we discussed, in principle, you could also have these mixed phase solutions where you gradually go from hadronic to quark matter, and then you wouldn't have this step here, but it would be kind of washed out. You would go gradually from here to here. So that's what you find when you actually solve these Oppenheimer-Markov equations numerically for different equations of state. And let me just walk you through these three different classes once more. So neutron stars have a characteristic mass radius curve then. I mean, so far this was the density profile, but as I said, again, I get a whole, for every mass, I get a whole curve, mass as a function of radius for a given equation of state. And that's what you get for neutron stars. You get this behavior here. And let me just point out that we kind of already estimated this behavior, because this part is actually this 1/r³ drop that we analytically derive. And if you do it properly, I mean, this is the correct curve, you see there are slight deviations, but roughly it's actually exactly that power model. And this is rather interesting because since this is such a strong dependence, what you find is that in the relevant regime of radii, the relevant regime of masses, the radius is rather insensitive. I mean, the mass changes strongly with radius, but if I just say, okay, I don't know what the mass is right now, then in this regime here, the radius is extremely narrow, in a very narrow interval, whereas very low mass stars are not relevant anyway. I mean, a mass of 0.5 solar masses doesn't really matter. That won't happen. That will be rather a white rock. And on the other hand, these guys here that are very close to the maximum mass, they are, well, maybe rather unstable anyway. So the relevant region really has this behavior that due to this strong power law dependence, the radius is rather insensitive of the mass. That's a really important point, and this will help a lot to actually determine, I mean, for instance, if we could measure the radius very precisely, this will help us to determine the equation of state, because this curve here is for one particular equation of state. If I pick another equation of state, this curve might be over here, right? At a rather different radius. So if we can measure the radius rather precisely, this tells us a lot about, what equation of state is actually realized. And so, first of all, I should also mention that this is not a realistic solution for a realistic equation of state. If you would use what we discussed initially, namely an ideal neutron gas, what you find is that the maximum mass is much lower, 0.7 solar masses, whereas in this case we get something above 2 solar masses. And by now we know that the maximum of any such curve must be above 2 solar masses, because we've measured one. I mean, we've seen 1 or 2 by now, very heavy neutron stars, and therefore we know any equation of state that would give us a curve that does not go up to 2 solar masses is ruled out by now. And that's also a very strong constraint. But yeah, the point is, nuclear interactions are really crucial. If we don't take them into account, we cannot explain the stars we see. So we really need rather strong interactions that give a rather stiff equation of state. I showed you this. I showed you this before. I mean, well, this is the pressure and gravity that are competing, and therefore we really need a very strong, stiff equation of state to get us to its really high masses. And I told you in the beginning, it's also the evolution that decides what mass the subject star has, and therefore it's not clear if you actually get to the maximum. If there's actually a somehow evolution mechanism, I mean, you know, these are created in a very messy environment, the core collapse, where you have a lot of kinetic energy, and it might be that you don't even get here to the maximum, because this is kind of the static limit. If everything would adiabatic, and you just add a bit more and more and more mass, you will get there. But in reality, you have a really dramatic process where you collapse this huge star to something tiny, and you have a lot of kinetic energy in the system, and then it's not clear that you actually reach the maximum that this curve gives you. So that's just a remark I want to make. But okay, that's what you find for neutron stars. These are the curves that you find for strange stars. And as I told you, in the case of strange stars, they are self-bound. You don't need gravity at all because you have the vacuum pressure that compresses the star. And also, 2 weeks ago, we also already derived a scaling relation for this case. And what we found was that the mass goes as r cubed. And as you see, you find exactly that. So in a regime where the vacuum pressure actually dominates, the star self-bound, you find exactly this. As you go to really high masses, then at some point the star becomes gravitationally bound. That means gravity actually overturns that, and this is this small piece here where it's bending over, and then again it becomes unstable. So that would be the strange star case. As you see, you find a qualitatively very different mass radius relation to these guys, which in principle could be something you could probe. But on the other hand, surely we cannot access this region here of the mass radius curve anyway, because they won't be neutron stars, but rather white dwarfs. And correspondingly, we only talk about this small region here, and that might then not be so dramatically different, right? I mean, we won't be able to map out the entire curve anyway. We just have a few sources, and so it's rather. It's not that easy to really, just from the form of the curve, determine what the star is made of. Okay, but in general, it has this rather different behavior. In the last class, I already mentioned are the hybrid stars, where only in the inner core of the star, the density is so high that we transform neutron matter into quark matter. And in this case, you have this phase transition, as I showed you before. And what you find then in the M(r) curve is that you go from this behavior of a neutron star at large radii and small masses at some point to the behavior that you will find for these hybrid stars. And that's also something we discussed last time. That's the relativistic Fermi gas. That would give you a relation M, or a scaling M proportional to R. If you remember last time we had this, and actually that's what you see. You see some, well, it's not perfectly linear, but some linear rise here in this regime. That means the scaling relations get us rather far as far as the qualitative aspects of the M(r) relation is concerned. And yeah, so in the case of these hybrid stars, you really would have kind of two qualitatively different regimes. In one case, the hadronic part dominates, the quark core might be there, but it's so small that it doesn't really matter as far as the mass or radius is concerned. And in the other case, where the quark core becomes really big and dominates everything. This is this branch. Okay, and I just want to mention it. In principle, I mean, what you can have, I mean, first of all, I should mention this part here, where M goes proportional to R, according to the naive stability criteria, shouldn't even be stable. But if you do the analysis properly, properly, you find that actually, yes, it is stable. So that's, I mean, otherwise we wouldn't even have to talk about it. But it's rather intricate to actually show this. And yes, they can be stable. And if you have phase transitions at really high density going to some complicated phase, what people found is that you can get even something more weird, maybe something that people call a third family of stars. Now, I've already showed you this NOR curve for white dwarfs, where you would have something here like this, right? And then you would have the same thing again for neutron stars, right? And what people found is if you have what you do when you go from here to here, somehow you have a new form of matter, right? Here it was the channel of electrons, here it was the channel of neutrons. If you have a phase transition to some high density phase, and that high density phase is very different, it has a strong first order phase transition, people found you can even get another branch. So kind of a star, which is still kind of a neutron star, with a core of exotic matter, but you can get solutions where you have a similar star with a smaller radius. And that's very interesting. These are the so-called twin solutions, and you only can get this if you really have something like this, where you have a strong first order phase transition, where you really somehow go from one form of matter to a very different form of matter. And this is very interesting because this could be, if you could find this observationally. If you find two stars with the same mass but different radii, that would be kind of a smoking gun. Then we would know these stars must consist of different forms of matter. One is on that branch, and that's not just a matter of evolution, whether that guy ended up on this branch or on this branch. That just tells you that in one case, one of them might have slowly accreted mass and then would have been on this branch, whereas in the other case something more dramatic happened that would have gotten the star to here right away. Yeah.
Would it be related to time, like their ages also?
Not really the ages, the evolution. It would determine how they got here. Because, I mean, surely, if you have a star here, it wouldn't just collapse to this. They're really both stable. And something dramatic would happen to get the star from here to here or vice versa, right? That means they really would have two very different evolutions, but otherwise they have the same mass, they're very similar. All I want to point out is, if you would see something like this, that would really be a very clear signature of that high density matter is not just neutrons, there's something else. So that's very, very interesting, and that's why people study this a lot these days, these twin solutions. And as I said, it's really very similar to this case. It's just not that you would have now a completely new particle, but just say this would be hadronic, this would be quartz, and you need the strong first order phase transition to really make them different enough to give you a new branch.
Can I ask one question?
Yeah.
If you said what was C then? C 1.3 ones and
C?
Yeah.
Oh, that's a parameter of this bag model. I mean, you remember, so the quark part of the star would be described by this simple bag model, and what people do is they just add a constant in front. I mean, you have this pressure, and they just say, okay, if we compute interaction corrections to the free gas result, what people find is that to leading order, all it does is it gives you some correction factor in front. And so people model this by just saying, okay, let's have a number in front. This is the simplest one that people did, I don't know, 30, 40 years ago, which is just the ideal gas result. And as you see, there you only get 0.7 solar masses. Don't worry what this is. This is just some inverse radius, basically. That's why it's kind of flipped, the whole curve. But, okay, this is just the first computation people did. But since then, they use all kinds of models, and as you see, for each model you get a different MMR curve, and they can be very different. I mean, these are all kinds of models. And by now we're starting to rule out some of them by the observations we have. I told you, for instance, the mass has to be 2 solar masses. That means this way we can somehow start getting rid of some of them that cannot provide 2 solar masses. But still, there are many options. Just to give you an example of what people come up with. And by now we also have curves like this here. This would be a curve that, I don't know, maybe I have a better plot for that. On another slide. But now we also have curves that actually come from observational constraints. And that's much safer than just, well, making up models and tuning. But by now we can actually get first constraints from observations, and okay, I'll come to that later. Okay, but as I said, we just don't know yet what the right equation of state is, and correspondingly we also don't know what a realized MMR curve is. Okay, so let me quickly come to rotation. I mean, so far everything was static. So far I just said, okay, what's the equilibrium configuration of when I put a lot of mass in a small volume, what will the gravity do, how will gravity shape it, and what's the equilibrium configuration. Now in reality, it's a bit more complicated because most of the neutron stars we see actually rotate, and they rotate pretty fast. I mean, some of them rotate really as fast as they can, and if you have something like this, if the star rotates very fast, what happens is that this otherwise spherical star becomes flattened. So if you solve the corresponding equations when you take into account rotation, what you get is something more like this, where the star becomes more, pancake shaped. I mean, really not pancake, but it will really be squeezed quite a bit. I mean, this is, for instance, the red curve is a neutron star if you assume it rotates as fast as it possibly can. And possibly can means if it would rotate any faster, it wouldn't be stable anymore, right? That's called the Kepler frequency, and if it would rotate at that frequency, I mean that frequency is a bit more than a kilohertz, usually, then it would look like that. That means it would be strongly deformed. As you see, for other forms of matter, it wouldn't be that dramatic. I mean, the reason is that the neutron star is very dilute, the outer parts are not very well out. I mean, the core part is very compact, but then as you go towards the surface, the density gets very low, and correspondingly you can easily smear that out. And this is kind of all the low density matter that makes the star blow up. In the case of a straight star, you don't have that. The density is rather uniform everywhere, and correspondingly rotation doesn't have such a big effect. I mean, it has an effect, but not as dramatic as in a neutron star case. Okay, and as I said, this is relevant because many of the stars that we see spin extremely fast. And first of all, we would expect this anyway, even for young stars, because of rotation, of angular momentum conservation. I mean, a huge star that rotates and all of a sudden contracts to something tiny, you would expect it to spin up dramatically. And as I said, in this case of old stars, we actually see them spin very fast, and we understand where this comes from because they accreted during their life a lot of matter which added angular momentum and spun up. Okay, and in this case, if you then look at the stability, what you find is that whereas usually you just have pressure and gravity in the game, in this case we also have centrifugal forces that can push outwards, and correspondingly you can have rotating stars with substantially larger masses. That means, whereas before, I mean, in these plots we found stars that could have masses somewhat above 2 solar masses, if you add in rotation and assume they rotate very fast, you might even go to 3 solar masses. And this is very important because, as I said, the spin changes during the evolution of the star. That means if a star initially spins very fast and then spins down, I mean, gets slower, the rotation gets slower, at some point it might become unstable, right? I mean, if it spins very fast, it can have a large mass, but once it spins down and gets slower, then the gravity might be strong enough to actually collapse the star. And this is something called a delayed collapse. So in principle, what you could have is that when an ordinary star, say, explodes in a supernova and has a core collapse, you would form a compact star that will still rotate very quickly. And then after some time, when it lost enough angular momentum, it might actually collapse to a black hole because the mass of the compact star is too big to be sustained at rest if it doesn't rotate anymore. And this would be very interesting because this would also lead to somehow a drastic event, basically a second supernova. And this is something that people look for, and that's very, very interesting. Then, yeah, the other thing is that I think that's maybe what I wanted to say here. Right, so the last point is that you can also have phase transitions from these spin changes. I mean, the most dramatic case I already told you about, it would collapse. But the other thing is that also, surely when you start with something like this, and then the rotation becomes slower, the star will be more compressed, right? I mean, you go from something big to something much more compact, and correspondingly the density increases in the star. And therefore, it could be possible that at some point in the evolution, you somehow reach an interior such a critical density where some new form of matter would arise, and you would have a phase transition. And in this case, you might actually have observable signatures, because, for instance, if the strange matter hypothesis is fulfilled, what this would mean that at some point, as the star spins down, the density would be big enough that the small quark core forms, and then it would just grow and grow and grow, because if this hypothesis is fulfilled, that's the absolute ground state of matter, and it would just eat up the entire star at that point, and it could be triggered by just spin down. And also that would lead to a rather dramatic energy release, so-called quark nova, and that's also something that would be very interesting. We could relate this to any of the observations we see of bursts or gamma ray emission that we actually see rather copiously. Okay, so I think I'll probably stop here. I guess I'm